Yes, dear student, now I start chapter 5 in this video. That is the chapter name is Magnetism and Matter. Magnetism and Matter. Before I start telling something about bar magnet, I request all my viewers to read introduction of chapter 5 from NCRT book. Good story of magnetism is given from what was the origin and when magnetism was discovered nearly 600 BC. The shepherd in island Magnesia noticed that their shoes having iron nails stuck to the ground, and that way the name of magnet has come from this Magnesia. There is a good story in that book. Please read for good knowledge and start reading NCRT book. Initially you may feel that I am not getting anything, but if you read a topic sincerely 2 or 3 times, you will get sufficient knowledge. Actually, NCRT book appears to be thin volume, but in thin volume there is lot of knowledge, lot of instructions, lot of informations are given. I have read many books, but what I find in NCRT is not found in those books. Please accept my request and start learning. You read only the introduction and other topics from this book also, although it appears that they are not useful for practical exam, etc. But somewhere they come in action. So now I start about bar magnet. First topic is bar magnet. So after the discovery of magnetism, the iron nails or some ore of iron like magnetite, which was later on given name as lodestone, means lodestone is leading stone, leader जो बनता है तो who tells the direction. तो नाम वहाँ से आया magnetite ore था, that was magnetite ore, magnetite ore of iron. And was given name lodestone because it was telling direction. Because these ores, having a piece of ore, when suspended freely, it was staying in north-south direction, and same phenomena was observed when the magnet or lodestone is placed on cork which floats in water. That also point north-south. So that way it was given the name. It is given in the book. Please read that. Now I come to bar magnet. Actually, bar magnet were prepared later on by different methods, and it was found that bar magnets have their magnetism concentrated at poles, which are called as North Pole and South Pole. Total concentration of magnetism at poles. And now in our terminology, these poles are found to be little inside, and distance between them is marked as 2a. The pole strength here we can represent by capital M. Here we don't write plus M minus M. This is center O. The center O. Now I will explain why this magnet is there. But remember here that magnetic strength is concentrated at poles. Magnetic strength of bar magnet is concentrated at poles which are little inside as shown in figure. As shown in figure. So, sorry, बीच में डिस्टर्बेंस हुआ. So I told you that magnetic strength of the bar magnet is concentrated at poles which are little inside, as shown in figure. This pole strength is by capital M. The pole strength is denoted here by capital M. Distance between poles. Distance between poles is called effective length of bar magnet. Here it is written 2A. It is here 2A. So from figure now I can say 2A into capital M is equal to, or you can write M is equal to 2A into M. M here, M is the magnitude of magnetic dipole moment of bar magnet. Bar magnet. Capital M I told is pole strength. As we know that unit of M is ampere meter square. So unit of pole strength is ampere meter. Ampere meter. Ampere meter. Unit of pole strength is ampere meter. This is some properties of bar magnet which I stated here. We represent like this, but there are other properties of bar magnet, like magnetic field lines of bar magnet. So here I will write, this M is also a vector. Magnetic moment is also a vector quantity, and we write it as 2A into M into n cap. So यानी कि n cap is a unit vector. Unit vector whose direction is from South Pole to North Pole. Direction of magnetic element of M is from south to north. Means if this is south bar magnet, north pole this way, south pole here, so M will be this way. Vector M from south to north. This is important here. Actually, these properties of magnet are very important, dear students. Now, magnetic field lines. Actually, some authors use magnetic lines of force, which confuses, because we will learn here. I have told you force on units I magnetic field is given by Q into B cross B. B is the direction field and field is meant by field lines. So this does not, this equation tells that force on moving charge magnetic field is not along the direction of field. So we avoid to write magnetic lines of force. So magnetic field lines, magnetic field lines of a bar magnet. So if you say here a bar magnet like North Pole, South Pole is there, so field lines of bar magnet are like this. In fact, like this. They enter South Pole and leave at North Pole and make even closed loops like this. The same pattern of field lines is there because of long solenoid also. Long solenoid also make and close like this, closed loop. Electric field lines, you have learnt, do not make closed loop. Electric field lines do not make closed loop, but magnetic field lines, don't call magnetic lines of force, it is magnetic field lines. They make closed path. And the property of field line are tangent at any point gives the direction magnetic field, and closer the field lines, stronger the field. Closer the field lines, stronger the field. You can read all such things in different books. I will tell you other properties like this. So this is pattern of field line of bar magnet. Electric field line do not make closed loop. I mistaking again. And here one thing more, magnetic field lines do not intersect, because if they intersect, then there will be two directional field at the point of, suppose they intersect like this. So one tangent here, other here. So field direction will not remain unique. So field lines due to a magnetic field do not intersect. Now why magnetism is present actually? In last chapter we have learnt lot of thing about the magnetic field, who produce magnetic field. You learned moving charges produce magnetic field. I told you the magnetic dipole moment with electron, moving electron. And every material here, every material has atoms, and with some material are there with which with every atom there is atom dipole. Every atom behave like dipole. So in case of iron or some other material, every atom has a net dipole moment. But you see, nail of iron does not show magnetism. Why? Because the atomic dipoles are randomly distributed. So net dipole moment is 0. These are totally random. These magnetic field lines are these atom dipoles are quite random, and therefore there is no net dipole moment. Like electric dipole, I will just write here. A bar magnet also experience torque in magnetic field. Due to that torque, if I place them in a field, if I use here outside magnetic field like this, so these atom dipoles try to align parallel to field. And if there is a net dipole moment, some still may remain random. So, but there will be a net dipole moment with this, and it will behave like a bar magnet. We prepare bar magnets from iron, ore of iron is there, permanent magnet, which is called anlico. Anlico used to prepare permanent magnet, that bar is placed for a long time in a uniform external magnetic field. So all atom dipole become parallel. To magnetize the bar, we place inside outside magnetizing field. So that make all atom dipoles parallel to the field. So this is something about bar magnet. Why iron bar behave like magnet? Because all atom dipoles become parallel and they are kept. There are certain material which can be easily magnetized. So they don't make permanent magnet. But the ore like alnico is magnetized with difficulty and hence not easily demagnetized. So now next topic, in next video I will start something more.